6.3 talks about the Schmidt process and the QR decomposition. We start off with the definition. A set of two or more vectors in a real inner product space is said to be orthogonal if all the pairs of distinct vectors in the set are orthogonal. So all of them, not one, all pairs of distinct vectors have to be orthogonal. An orthogonal set in which each vector has a norm of 1, remember norm means magnitude, its length is 1, is said to be orthonormal. Now, if S consists of the following vectors, if this is an orthogonal set of non-zero vectors in the inner product space, then S is linearly independent. And remember, we need linearly independent if we want to find bases. Every non-zero finite dimensional inner product space has an orthonormal basis. Now, let's start with this first. If S consists of the following vectors, if S is an orthonormal basis for an inner product space V, that means if the magnitude of those is 1, each one of those, and if U is any vector in V, then U can be written as the linear combination of those in the following format. You take U would be the inner product of U times V multiplied by vector V1, then U, the inner product with vector 2, V sub 2, times V sub 2. So this is going to turn out to be a vector. If those vectors are just orthogonal, they're not orthonormal, that means the magnitude of those is not 1. If this is, again, a basis of the inner product space V, and U is any vector, then if you want to find U, that should be a linear combination of those, except now you're going to take identically to what you did right there, except you're going to divide that by the magnitude of V1 squared to ensure that it has a norm of 1. We'll apply this and we'll talk about that when we get there. Here's a vector. Here's a set of vectors. This is like V sub 1, V sub 2, V sub 3. In each part, determine whether the set of vectors is orthogonal and whether it is orthonormal with respect to the Euclidean inner product of R3. Well, first things first. If I take the magnitude of V1, that is the square root of, you square that, that's 1/2 plus 0 plus 1/2, that's 1, it checks. This vector right there, the magnitude, call that V sub 2. That is, if you square that, that's 1/3 plus 1/3 plus, when you square that, it becomes a positive 1/3, that's a 1. And if you take the magnitude of V sub 3, that is the square root of, square that, that's 1/2 plus 0 plus 1/2, which is 1. So those satisfy the magnitude of 1. Now this is the first case. The second case is checking if these are orthogonal, and you could tell that the inner wrong vector. You could tell that the inner product of those is going to be negative. So if you take you could tell that that's not going to be a 0. That's negative 1 over radical 6 plus 0 minus 1 over radical 6, which doesn't equal 0. So this set is not orthogonal, and therefore it is not orthonormal either. It could be orthogonal, and if the magnitude doesn't equal 1, that will be an orthogonal set. to be an orthonormal, they have to be orthogonal to each other, and the magnitude of each should be a 1. So if you could see something like that, automatically you could figure that out, because the dot product, pretty much you could do it visually. And you notice here it does work, because that and that will zero out. So go straight for the vectors that have the exception and show that, and pretty much you're done. No need to do the busy work. Here's another vector. If I take the magnitude, again, call this v sub 1, this v sub 2, this v sub 3, magnitude of this is going to be, well, again, you could do it visually, but let's write it out. That's 4/9 plus 4/9 plus 1/9, which is 9/9. That's 1. So the norm of 1 is matching for v1. It has to work for all of those. Again, that is 4/9 plus 1/9 plus 4/9. That also checks. And if you take the magnitude of v3, that is 1/9 plus 4/9 plus 4/9, and that's also a 1. That checks. Now what we have to check, are they orthogonal to each other? Well, let's see. If I take v sub 1 and v sub 2, that is 4/9 minus 2/9 minus 2/9, which is 0. If I take v1 and v3, the inner product of those, that's those two, that is 2/9 minus 4/9 plus 2/9, that is 0 as well. And if you take v sub 2 and inner product with v sub 3, that would be those two, that is 2/9 plus 2/9 minus 4/9, that is 0. So this set is orthogonal number 1, and orthonormal. So the checking is not that bad. I just need to adjust those quickly. So given vectors, that's how we check them. That's not that bad. When I get to number 4, I notice they're talking about matrices. Well, call this A, B, C, and D. Here you have to do a bit more work. Well, first things first, if we take AB, well, that is 0 plus 0 plus 0 plus 0, which is 0. That checks. If we take AC, that is 0 plus 0 plus 0 plus 0. That checks. If we take AD, that is 0 plus 0 plus 0 plus 0. Again, the product of those. That's 0. That checks as well, but that's not enough. I did A. Now I have to do B, C. That would be those two. That is 0 plus 4/9 minus 2/9 minus 2/9. That is 0 as well. That checks. I'll take BD. That is those two. 0 plus 2/9 plus 2/9 minus 4/9 equals 0. That checks. And if I take CD, 1, 2, 3, 4, 5, 6, that would be those two. That is 0 plus 1/3, 2/9 minus 4/9 plus 2/9. That's also 0. So the set is orthogonal. And of course, for a matrix, it doesn't make sense for you to talk about its length. There is no such thing. Number 6, show that the column vectors of A form an orthogonal basis for the column space of A with respect to the Euclidean inner product, and then find an orthonormal basis for the column space. Well, let's see how we're going to do that. V sub 1 would be 1/5, 1/5, 1/5. V sub 2 would be the second column, and the third would be 1/3, 1/3, negative 2/3. Basically, that's what we're doing. And now we're going to go ahead and check the first part. And the first part was show that they are orthogonal. Well, let's see. Those two, that is negative 1/10 plus 1/10 plus 0, which is 0. It checks. Not enough. I have to do all the combination. First and the last. That will be 1/15 plus 1/15 minus 2/15, which is 0. It checks. And if I take the second and the last, again, all the combinations, that would be, nope, I'm messing up, those two. And that is negative 1/6 plus 1/6 plus 0, which is 0. So all of that check, that's good. They are orthogonal, right? And if they are orthogonal, they are linearly independent. According to the theorem, so we know that they form bases. For the column space. Of matrix A. Now, the second part, I forgot what it asked, what did it want? It was, and then find an orthonormal set for the column space. Well, take V1. I need, okay, I'm going to move this down here. Okay, and here, for the second part, I'm going to take V sub 1 divided by its magnitude. So the magnitude of V1 is 1/25 plus 1/25 plus 1/25. That is square root of 3/25. The magnitude of V sub 2, that is 1/4 plus 1/4. So that is the square root of 1/2. And the magnitude of V sub 3 is the square root of 1/9 plus 1/9 plus 4/9. That is the square root of 4, 5, 6/9, or simply divided by 3 2/3. So if I take V sub 1 divided by its magnitude, V1 is 1/5, 1/5, 1/5. If I divide by a fraction, that's the same as multiplying by the reciprocal, so that's 5/3, and that turns out to be simply 1/3, 1/3, 1/3, and now you could tell that the magnitude of that is 1. And if I take V sub 2 divided by its magnitude, well, V sub 2 is negative 1/2, 1/2, 0. And if I divide by that, you're multiplying by radical 2/1. That turns out to be negative radical 2/2, radical 2/2, and 0. And again, if you find the magnitude of that, that turns out to be 0. Of course, you could write it as 1/radical 2 if you want, if you rationalize. It doesn't really matter. And V sub 3 divided by its magnitude turns out to be v sub 3 is 1/3, 1/3, and negative 2/3, and its magnitude multiplying by the reciprocal. And by the way, there's nothing wrong with you leaving the answer like that. That's fine as well. But most likely the back of the book will say that's radical 3 over 3 radical 6. You could radical 2, I was rationalizing in my head. That's radical 3 over 3 radical 2, and that is negative 2 radical 3 over 3 radical 2. You could rationalize those if you want, but it doesn't really matter. It's the same thing. And we could tell that those are orthonormal bases for the column space of A. Those three vectors, you could list them there. So call this U sub 1, U sub 2, and U sub 3, and you could say there they are. And that's pretty much all we have to do. Now, here it says use theorem 6.3.2 to express this vector U as a linear combination of vectors v1, v2, v3 that we just did in exercise 7. I copied what's in exercise 7. That will be these three vectors. Well, here what we want to do, and if you recall, we're talking about this bottom part. Let me double check really quick. Yeah, reason for that, the magnitude of this vector, it tells you to use b, but the magnitude of that vector is 9 over 25 plus 16 over 25, which is 25 over 25. That's a unit vector. Same deal here, and the magnitude of that is 1. So since those are unit vectors, even if they gave me a choice, by those form orthonormal bases, that's the formula I use. And the way it works, I'm going to take U, inner product of U with V1 times the vector V1. So U is going to equal the inner product of U with V1 plus U V2 V sub 2 and U V sub 3 V sub 3. So U would be, let's see, the inner product of, and here let me put it, okay, here, this to this, that will be negative 9, okay, that will be negative 9 divided by 5 minus 28 divided by 5 plus 0, v sub 1, I'll clear that in a minute. And here when I do the inner product of those, that would be 12 over 5 minus 21 over 5 plus 0 v sub 2 plus 0 plus 0 plus 4 v sub 3. And if I clean these up, I'll get the vector to be negative 37 over 5. If I make an error in the addition or subtraction, you know what that means. Just the idea. Let's see, 21 minus, that's 9, and it's minus. And 4 v sub 3. So that's what U would be. Linear combination of those three. And that's all we need for this section. We're going to stop here. This is all we need for what's to come.